To proceed here, we need to know the initial and final wave functions. We are most interested in the transitions between an initial valence band state and a final conduction band state. We presume that we can write them as single electron Bloch states. And to calculate matrix elements, we have to normalize the way that we write down these wave functions here. So we're going to have to figure out how to normalize Bloch functions. We're going to allow these wave functions for the initial and final states to have normalization constants Bi and Bf. And with those choices, then our initial state is going to be this Bloch form with a normalization constant we still have to figure out. And similarly, the final state is going to be this Bloch form, again with a normalization coefficient we need to figure out. So here and below, for simplicity, we're going to presume that these unit cell functions in both the valence band and the conduction band do not depend on k. We don't have to make this assumption, but it turns out to work fairly well for most of the transitions we'd have to work with, and so we'll make that for simplicity right at this point. It just saves us some complications. And this is indeed a good approximation for what we would call an allowed process, where the matrix element for this particular transition is not 0 or nearly 0. So given that, again, for simplicity in our algebra, that allows us to omit the k subscripts on both of these unit cell functions. We do, however, allow the conduction and valence band unit cell functions to be different. In fact, they really have to be different here or we're not going to get good optical absorption. So this unit cell function in the valence band, we're seeing it doesn't vary very much with kV, but it's different from this unit cell in the conduction band, which we're also presuming for simplicity doesn't vary very much with Kc. So first of all, we get to make a choice here. We're going to choose these parts of this function overall to be normalized over a unit cell volume. That is explicitly for the valence band function, for example, this unit cell function, we're going to presume that we normalize this particular unit cell function so that if we only do a volume integral over the unit cell to do its normalization, it will be 1. So we're presuming that, and we will set that normalization to be 1. And we'll do the same thing for the conduction band unit cell function. Hence, normalizing the complete wave functions, we have, for example, for the initial wave function, our criterion for normalization is integration over the entire volume of the crystal of the wave function times its complex conjugate. Well, that should be 1. So, using the forms that we wrote down for the wave function, Bi times the unit cell function times the e to the I k dot r, then performing this integral here, normalization integral, will give us Bi squared times the integral of just the unit cell parts over the entire crystal volume, because these two exponentials multiply to 1. Well, we know what the unit cell functions integrate to over a unit cell. That's just 1. And the volume here is just the total number of unit cells times the volume of the unit cell. So this integral over volume is the same as n times the integral over the unit cell. Integrals over any one unit cell here give us the same thing. It doesn't matter which unit cell we choose. So the total crystal volume is n times the unit cell volume, and we know the answer to this integral by definition for any given unit cell. And we chose that to be 1. And so this normalization integral for this function, with our choice that we made here for the unit cell function normalization, is just Bi squared times n. And hence we have that this normalization constant here, the Bi, is 1 over root n, or we can choose it to be 1 over root n. So the matrix element for Fermi's golden rule then, using these normalized functions, and we got the same normalization for the initial state and the final state, the method of calculating those normalizations would be the same. Then with our wave here, which had our optical electric vector E in it and our amplitude of the magnetic vector potential and the propagating wave, that was A dotted into the P operator, then gives us a matrix element for Fermi's golden rule in the following form. So here's our way of writing out that matrix element using Bra-and-Ket notation. And down in here is our entire perturbing Hamiltonian as a function of R, so some constants out front. And then the e to the I k optical dot R times the unit vector in the electric field polarization direction dotted into the momentum operator. Here's all that down in here. Here's the initial wave function. The normalization constant has been brought outside. And here's the final wave function. Again, the normalization constant has been brought outside. So this is the integral we need to work out now to work out the matrix element for Fermi's golden rule. Now, we're interested in transitions involving states near to the center of the Brillouin zone. That's just an assumption we're making here. So, therefore, both of these wave vectors of the initial and final states are themselves going to be much, much smaller than the size of the Brillouin zone. It's just a simplifying assumption we're making here. Now, strictly speaking, this momentum operator, minus IH bar times the gradient, operates on every part of this wave function inside the matrix element. But with these small values of kV, this e to the I k dot r part changes very slowly compared to the rate of change of the unit cell part. The unit cell part changes within a unit cell, so therefore it's a rapidly changing function. This e to the I k dot r changes over only some relatively large number of unit cells if we're looking for a substantial change in it, precisely because we've said we're working near to the center of the Brillouin zone. So when we take this derivative here, taking the derivative of the unit cell function and the propagating wave that's part of the Bloch function here, the quantum mechanical wave, then of course, we should get two terms here. We should get the term that comes from the momentum operator operating on the unit cell, multiplied by the e to the I kv dot r, which we could take outside. And then the other part we should consider is the unit cell function times the momentum operator operating on this e to the I kv dot r. But by assumption, this e to the I kv dot r is not changing very rapidly, and so compared to this term here, this term is going to be very small. So we forget that term. And we're left only with this one term here. That's an approximation, but as long as we're working near to the center of the Brillouin zone, this approximation is going to work. For definiteness, we'll now choose a polarization direction, that's this unit vector E, to be in the x direction. That's going to be at right angles to our propagating wave, so that's a valid electromagnetic wave. And with this choice and our approximations so far, this matrix element here and the formula we just wrote out before is going to simplify somewhat. So we can multiply together all of the complex exponentials and put them all in this term here, and we're left with this part of the integrand, which is where all the real action is taking place in the momentum operator. Because this optical electric vector was in the x direction, the dot product of that with the momentum operator only leaves us with the x component of the momentum operator in this case. Now, the optical wave vector corresponds to wavelengths that are typically hundreds of nanometers or more, even inside the material and allowing for large material refractive indices. A typical crystal unit cell size is something more on the scale of half a nanometer or something in there. So this optical wave is varying also very slowly over a unit cell. Hence, since we have already restricted both the wave vector of the Bloch part of the initial valence band function and of the final conduction band function to be both small, then this entire factor here varies very slowly over the length scale A of a unit cell. As a result, we can approximately separate this integral here, that we wrote out before, into a sum of integrals over a unit cell. And we'll treat this term here as being approximately constant within any unit cell. It's varying very slowly over the size scale of a unit cell. So with that, we can take these out as constants here, a different one for every unit cell, but all we're left with to perform here as an integration is within any one unit cell to work this out. And of course, this integrand is the same in any unit cell. So this integrand we can pull out of the integral as a constant and turn the integral just into a sum of these complex exponentials here, and just using the value of r in the middle of a unit cell. We're saying this factor within any given unit cell doesn't vary very much inside the unit cell, so we can replace it by its value, say, in the middle of the unit cell, and we can index that using the crystal lattice vectors. So these are all of the unit cells here. M is an index for the unit cell. So this we've pulled out as something we can work out separately here. Rm is the position of the center of the mth unit cell, and explicitly this matrix element here is just this integrand integrated over a unit cell. And we will call that PCV. This is a matrix element that comes up in many contexts in working with semiconductor physics, not only in this optical context. It tends to come up in discussing band structures, for example. Now, the summation inside this formula we just ended up with is going to average to 0 unless the sum of all three of these wave vectors is 0. Otherwise, we have a rapidly oscillating function when we sum over the entire crystal here, and it will in general average to 0. This condition here that we expect this wave vector minus that one plus the optical wave vector to be approximately 0 essentially corresponds to conservation of crystal momentum. We're saying that for transitions to be possible, the sum of all of these three, which we can think of as momenta, if we put h bar in front of them, we can think of them as momenta of some kind. This criterion that the sum of these three must be approximately 0 is something that looks like the idea of conservation of momentum. So unless we get this apparent kind of conservation of momentum here, the transition matrix element will be essentially 0. Note that this effective momentum conservation is something that comes out of the calculation. It's not something we put into it. And we have to be careful here because h bar kv or h bar kc is not really the momentum of the electron. It's the momentum associated with the envelope function part of the electron's motion. But still, this has a look of momentum conservation. But remember, we did not put momentum conservation into the calculation. It's an effective momentum conservation that came out of the calculation. In this case, if we set these wave vectors summed together to 0, then this summation here just becomes the sum over all the unit cells of e to the 0, and that's n. Hence, finally, using the expression we had before, turning this with momentum conservation-like behavior into just n, then the n's cancel. We're left with the PCV here, and this is our final expression for the matrix element between initial and final states, provided that these three wave vectors add up to 0, and that looks like momentum conservation. Otherwise, this matrix element is 0. So we're now forcing the final wave function to have a wave vector that is such that this all adds up to 0. And then Fermi's golden rule gives us a transition rate. This was our formula for Fermi's golden rule. So substituting in this answer for our matrix element gives us this result down here. So if we have some instant optical wave of frequency omega, angular frequency omega, wave vector k optical, and magnetic vector potential amplitude A naught, for some initial state of energy EI and a Bloch wave vector kV in the valence band, and a final state of energy EF and Bloch wave vector kc in the conduction band. If and only if the sum of these wave vectors, kV minus kc plus k optical, is equal to 0, we will have what we call a direct transition rate. And here's the formula that we have come to for that. The direct here refers to this effective momentum conservation. To summarize so far, we've made use of the facts that, first, the electron wave functions in the crystalline semiconductor are in the Bloch form, and second, that the optical wavelength is much larger than the unit cell size. Then we've used Fermi's golden rule to calculate transition rates for optical absorption. We have found that to get this direct optical absorption, the envelope function wave vectors for both the initial and final states have to be essentially the same, corresponding to a vertical transition on our diagram. Since the photon has negligible momentum on the scale of the Brillouin zone, this concept effectively looks like the concept of conservation of what we could call crystal momentum, that is, h bar times k, and is consistent with h bar times k being the effective electron momentum in a Bloch state. We did not start out by any presumption of conservation of momentum in any form, but we ended up seeing something emerge that is very like conservation of momentum. Note that this effective momentum, h bar k, is not actually the full momentum of the electron. Rather, it's more like the effective momentum of the quasi-electron that is described by the envelope function. The actual momentum of the electron also involves a spatial derivative of the unit cell function, not just of the envelope function. Note also that this transition rate we've just calculated is proportional to a squared matrix element, so PCV modulus squared, the optical intensity, that's watts per meter squared in the light beam, which turns out to be proportional to the square of the magnetic vector potential oscillation amplitude, and hence it's proportional to the average arrival rate of photons in the semiconductor per unit area.